Welcome back to Shapes, all about shapes. Didn't know you could learn so much about shapes, did you? Last time in 8.7, let me flip this here, we were talking about transformations. We talked about reflections before, and we talked about translations, which means just sliding a shape over, rotations, which 90 degree and 180 degree rotations. So today is our final section of this chapter, and we're still talking about shapes. So check this out. This triangle and this triangle, they are both triangles. Yes? Yeah, they're both triangles. I mean, this one, maybe I should make that a closed polygon. There it is. So this is a small triangle, and let's pretend that this triangle and this triangle are drawn to scale. They are the same shape, right? Are they the same shape? Let's say this angle is the same as that angle. This bottom one's the same as this bottom one. Yeah, they're the same shape. But are they the same size? No, they're not the same size. One is much smaller than the other, right? So there's something that's the same about them, but there's something that's different, right? So what is that? Well, I'll tell you. And I've kind of already told you with these congruence marks. These are the same shape, and their angle measurements are exactly the same. But their side lengths are different, right? This side length is a lot longer than that little side length. But this angle is exactly the same size as that angle. They're both about 30 degrees. And both of these are about 50 degrees, and so on and so forth. So that's what we're talking about today. Similarity and dilations. We would call these two triangles similar. And the symbol that we use for similarity, they're not equal, they're not congruent, they are similar. That's the symbol. Okay. So check this out. They have the same shape, similar polygons. This works not only for triangles, but for quadrilaterals and other shapes. They have the same shape, but they're different sizes. Okay? So, there is a certain way that you must write a similarity statement. This is a similarity statement. It's saying one polygon, in this case a triangle, is similar to another polygon. So, you have to write the corresponding vertices in the right order, like we've talked about before. So right here, they said triangle ABC is similar to, now in this smaller triangle, A is the same vertex as what in this smaller triangle? Well, look at that angle. It's got the 2 marks. This one has the 2 marks. So A and X. Now they've lined these up nicely so that it's the bases are both, on the bottom like this. But they're not in your assignment, or like look at this example. They're not always lined up perfectly for you. So when you make a similarity statement, if you tell me something is similar to something else, make sure you've got the right vertices in the same order. So A, B, C, X, Y, Z. Okay? Now, what does this mean? If two polygons are similar, you have to know these two details. The corresponding angles are congruent. 90, 90, whatever, whatever. Okay? A and X, they're congruent. C and Z, they're congruent, and so on. So corresponding angles are congruent, but there's one other thing that's going to be very useful. Corresponding side lengths are proportional. So if you do, I'm going to call this the big triangle, this one the small triangle, okay? So 8, and I think let's see here. 8 over 4, because BA or AB corresponds to XY. 8 over 4 equals, put this where you can see it, 8 over 4 equals, so big one over little one, corresponding little one, could be the same as 10 over 5, right? Big one over corresponding little one. Is 8 over 4 the same as 10 over 5? They better be, or these aren't similar. But we already know they are similar, so they should be proportional. And 8 times 5 is 40, 4 times 10 is 40. Yeah, that works. Which is the same as 6 over 3. Big right side over smaller right side. So all of these proportions they've written right here are true for these similar triangles. Okay, so let's see what this example tells us down here. Tell whether the television screens are similar. Well, to be similar, remember, to be similar, you have to meet these two criteria. 1, all the angles have to be the same. 2, corresponding side lengths have to be proportional. So let's check those two. Are all of the angle measurements the same in these two rectangles? Yes, they are. They're all 90, 90, 90, 90, 99. So we're good there. So that's what they wrote here. 2, are the corresponding side lengths proportional? Well, 30 over 18, right side over right side, should be equal to bottom 40 over bottom 24. And they do the math here, 30 times 24, 720, 18 times 40, 720. Yeah, they're proportional. So notice how they write this similarity statement. Since it's not a triangle, we don't have like a symbol for quadrilateral. So they just put ABCD is similar to EFGH. ABCD similar to EFGH. Okay, now, how could you find an unknown side length? That's what I'm going to show you right here. Okay, let me fold this paper over so I can use a clean edge. All right. We know from the instructions that this triangle is similar to this triangle, and we're supposed to find the value of y. So what you guys have to do is you have to set up a proportion. So where do we start? Let's start with some numbers we actually know that they're listed here. So 10 and 5. 10, does LM correspond with PQ? Yeah. All right. So 10 over 5 is equal to, that's the big triangle over the small triangle, y, big triangle, over the small triangle corresponding side, 12. Okay, so 10 times 12 is 120, divided by 5 is 24. Y equals 24, and that's what they have here. Okay, your turn now. If this one was similar to this one, which it says they are, find the value of x. Well, this one is, remember, they're going to try to throw you off, okay? A, that point corresponds with what point over here? A looks like it corresponds with F. And then this big point out here, H and C. The smallest segment is AB. Smallest segment here is FG. So let's do it this way. Let's say x over, and it doesn't matter which side you start with. You can start with the big to small or small to big, as long as you keep it the same on both sides of this equal sign. Okay? So x over, what's the corresponding side over here? X. It looks like the corresponding side, this is the second smallest side, looks like. It's going to be this, 16. So x over 16 should be the same as 4, the smallest here, over the smallest here, 8. Okay, always do corresponding measurements when you make up these ratios. That corresponds with that, this one corresponds with that. I did small quadrilateral over the larger one, so I do small over the larger. Alright, so now let's reduce this. This 4 over 8 is the same as 1 over 2. Now 16 times 1 is 16 divided by 2, x equals 8. There we go. Not so bad. Now what's cool is you can actually use this method. In fact, surveyors and different people use this method to find the distance across a river without actually traveling across the river, or the height of this tree without actually measuring it. And here's how they do it. This triangle is similar to this triangle. So you're standing here, you're 5 feet tall, and your shadow is 7 feet long. This height of the tree is, we don't know, it's x, and the shadow is 14 feet. So, we know they're similar because this right angle, you're standing straight up, the tree's standing straight up. These angles are the same. These angles over here are the same because the sun is shining from up here, and it's hitting this at the same angle it's hitting that. Okay, so these two angles are the same. And in a triangle, it all has to add up to 180, so we know these two angles are the same, so we know these are similar triangles. Okay? Now you wouldn't have to figure that out, they would just tell you in the problem. The triangles formed are similar. Okay, that's nice. So, let's just make a proportion. Let's do 5 over x. Okay, small triangle over corresponding big triangle measurement. 5 over x should be the same as 7 over 14. So, 5 times 14 is, I don't know, 70 divided by 7, x equals 10. You just found out the height of this tree without actually measuring the height. You would have had to measure your shadow and its shadow, and then you can find the height of it. Kind of cool. You can find the height of like skyscrapers with this method, and measuring the length of the shadow, or flagpoles. So, kind of nifty. Let's see if we're right. Yes, the tree is 10 feet tall. Okay. The next area that we got to discuss in this section, then we'll be done, are called dilations. And let me just refocus this for a second. Alright, so have you heard of your pupils dilating? So if there's a bright light shining in your eye, your pupil will shrink. I believe it's shrink. So it doesn't let all that light hit your eye, right? And then when you come into a dark place where you can't really see well, your pupils will expand. So we call that dilation, shrinking or expanding. So notice that with these shapes, we're shrinking some shapes and we're expanding some shapes, right? So we're going to talk now about how you can shrink them and how you can expand them. So let me read this. Pay close attention, okay? This isn't above you, but you need to pay close attention to this concept. A dilation stretches or shrinks a figure, meaning expands or shrinks a figure. Okay, a dilation goes either way. The image created by a dilation is similar to the original figure. Okay, so remember that word? You have the original, and then you have the image. The scale factor of a dilation is the ratio of corresponding side lengths. The ratio of corresponding side lengths. We'll talk about that in a sec. In this course, the center of dilation will always be the origin. Okay, cool. So, I want you to notice this word scale factor. Factor is important. What is a factor? Please tell me you know what a factor is. It's part of a multiplication problem, right? 5 times 10, 5 is a factor, 10 is a factor. They make 50, which is the product. So this scale factor is always part of a multiplication problem. You're always going to be multiplying coordinates by a scale factor. So, here we go. To dilate a polygon, or a shape, okay, multiply the coordinates of each vertex by the scale factor k and connect the vertices. We always use this variable k to represent a scale factor. So if you've got like 4, 1, and that transforms into, that point transforms into the point 8, 2, because you expanded it, you multiplied those original coordinates by some scale factor. Can you figure out what scale factor we multiplied them both by? Multiplied them both by 2. K would have been 2 in that problem. So let's take a look at this. It's not so bad. Watch this. Kind of cool. Quadrilateral ABCD has vertices, la, 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 la. Okay, so let's find that. Blue is the pre-image. It's the original. Blue is the original. Red is the image. So this original has these vertices, -1, -1, etc. Dilate it using a scale factor of 3. Guys, this isn't rocket science. Using the scale factor of 3 just means multiply every coordinate by 3. That's it. K times the x coordinate, k times the y coordinate. K in this case being 3. So, they list the original vertices and they multiply each one by 3. So -1 becomes -3. -1, -3. 0 times 3 is still 0. 1 times 3 is 3. 2 times 3 is 6, and so on and so forth. Then they plot these new points, and then look what happens. When they plot those points and they connect it with the red pen there, does this big red shape look like a dilation or an expansion of the blue shape? Yeah, totally. So, pretty cool, huh? I don't think I need to do another example of that. It really is quite a simple concept. I'll just give you one warning. If you multiply a number or some of these coordinates by 5 or by 10, if you multiply something by something else, usually you're making it bigger, right? If I got this distance and I multiply it by 2, it's twice as long. Or a scale factor of 5, it's 5 times as long. But if you multiply by a fraction, meaning or a decimal somewhere in between 0 and 1, like 0.2 or 4/5. If you multiply something by a fraction there between 0 and 1, you make it smaller. You make it shrink. So you might encounter that in this section. Scale factors don't always make something bigger. Sometimes they'll make it smaller. And I was going to check for one more thing here. They might want you to find the scale factor, which we haven't talked about. So let's see if they actually have you find scale factor. Nope, they give you the scale factor there. They give you the scale factor. Here's a challenge problem to find the scale factor. You can turn this video off now if you want, or you can watch this last problem. It might be assigned to you, I don't know, but it's nothing crazy. It says, name 2 similar polygons in the diagram, find their scale factor. Well, AFB, triangle AFB, see it, this little one, is similar to triangle AEC. AEC. You see that? AFB is similar to AEC. Okay, now to find, oh well. Now to find their scale factor, remember in that blue box, it said, I'll just read it to you, the scale factor, or not in the blue box, but above that, scale factor of a dilation is the ratio of corresponding side lengths. All I got to do is do the ratio of corresponding side lengths. One ratio. That's it, guys. One ratio to find the scale factor. So 5 in the small one to, would it be 5 in the big one? No, it'd be 5 plus 5. Okay, 5 to 10. the scale factor reduces to, I shouldn't have circled that, should circle that, 1/2. So from the big to the small, scale factor is 1/2. Now I could have written it the other way around. If you're going from small to big, it would have been 2/1, which just equals 2. All right, so that is that. Dilations and similar polygons. Have a blast.